Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's challenging level puzzle, and it's called Synergy by Michael Lefkowitz. And here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit, such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. All arrows act as both modular arrows and entropic arrows. Now, what are modular arrows and what are entropic arrows? A modular arrow, a digit on an arrow, counts how many cells in the indicated direction have the same remainder mod 3 as itself, including its own cell. So that means this cell counts how many of these 8 digits have the same remainder, mod 3, as itself. So for example, this could be 5 if 5 of these digits would have the remainder 2 mod 3. So we're basically, what does that mean? It means if you divide by 3, you have a remainder of 2. So you could have something like this be 5, 2, and 8. This be 2 and 8 here, and these are non-2 mod 3 digits, which would be 2, 5, or 8. Then this would satisfy this cell as a modular arrow. And that's an example of how a modular arrow works. What about entropic arrows? A digit on an arrow counts how many cells in the indicated direction are in the same entropic group, which is low, middle, and high digits, which is the low digits being 1, 2, 3, middle digits 4, 5, 6, and the high digits being 7, 8, 9, as itself including itself. So, for example, we have 5, 5. Say we had a 6, 4, and a 4 here. Then this would satisfy both the modular arrow aspect and the entropic arrow aspect. Because along these 8 cells, because it sees the direct cells in this direction, including itself, how many digits are give you a 2 mod 3, are 2 mod 3 digits? Well, you have 2, 8, 2, 8, 5, and 5 here. That's 5 digits, which are 2 mod 3. How many digits are mid digits in these 8 digits? We have 4, 5, 4, 6, and 5. That's again 5 digits, which satisfies the middle set of the entropic arrows. And those are all the rules. If you'd like to play along, there's going to be a link in the description. And now I'm going to get started. Let's go. Okay. Anytime you have a digit in a row that's pointing in a row or column, the most you can ever have of the same entropic set or the same modular set are 3, right? Because you can have only 3 of the same entropic set and only 3 of the same modular set. So these 3 digits, all pointing in a row, must be the digits 1, 2, and 3. That means the rest of the column cannot be 1 through 3. They have to be 4 through 9. And this digit points at 5 cells in total, so this can't be 4 or 5. It can't be 6 through 9. This is again 1 through 3. We have 1 through 3 here as a possibility. This points at 4 digits at most. This points at 1, 2, 3 digits at most. Now, the thing is, can you ever have 9 on an arrow? I think the answer to that is no. Because it has to have 9 of the same entropic set, which would be 7, 8, 9, and 9 of the same modular set, in those digits that it sees. But 789 is necessarily different from 369, which are the modular sets. So 9's not going to work. 8 has the same problem. I think 7 also has the same problem. 8 would have to point at 8 digits, which are 2 mod 3, so that's 2, 5, and 8. And they would also have to point at 8 digits, which are entropically the same set, which would be 7, 8, and 9. The only overlap is the 8. So that means you have 8 digits of I guess it depends how many different boxes it goes through. I'm thinking about specifically, though, these two boxes here. Sorry, these two main diagonals. So 8 can only have 2 other 8s on there. So that's 3 8s. If you have 4, you have to have 5 other digits, which are going to be essentially the same entropic set, and 5 digits, which are going to be the same modular set. But those are distinctly different sets. So 8 does not work, because that would be 3 plus 5 plus 5, which is 13 digits that it would have to point at. And there's no way you can point at 13 digits. What about 7? 7 also doesn't work, because 7 can again point to only 3 7s on the main diagonals. That leaves 4 more for the entropic sets and 4 more for the modular sets, and those are distinctly different sets, right? The modular set is 1, 4, 7. The entropic set is 7, 8, 9. Obviously, 1 and 4 do not equate to 8 and 9. So on one of the main diagonals, you can never have a 7, 8, or 9. You could, however, have a 6 if you're pointing at 9 digits. Because 6 could point to 6 and 6. So that's 3 for the main. And then you have 3 more for the other modular set, and 3 more for the other entropic set, which does work here. So this is 1 through 6. But since this is on the main diagonal, but it only points at 8 digits, this has to be 5. Because you can't have 3, 3, and 3, right? It's 3, 3, and 2 at most. So that's 1 through 5. Can this actually be 5? I think the answer to that is probably not. If you have 5, you have 2 other 5s that can be here, and then 2 other unique digits. So that's 3 5s and then a 4th one. But you can, if you try to have 2, the other 2 are not going to be of the same modular set arrow if they're entropic, or they can't be the same entropic set if they're modular. So this cannot be 5, it's 4, guaranteed. This, then, cannot be 1. If this is 1, that means it's one of the same modular set as itself, but it already has a 4 there. So that would be 2 of the same modular set, so this cannot be 1. So this it can't be 3 then. 3 would not have the same modular set in that, so this has to be 2. So this must be 2, that must be 2 of the same modular set and 2 of the same entropic set. Well, 4 doesn't satisfy either of those. So we're going to make these low, medium, and high for now. So this is low, these are low. So this must be the same modular set and same entropic set, so these are both 2. So this is low, that means this cannot be 2 here. This can't be 1 because it already sees a 2 in that direction. So this must be 3, which means this can't be 3 here. This cannot be 1. If this is 1, that means these have to have 2 low digits here, which is not possible because we already have a 3 in this box. And therefore, we'd have 4 low digits, which is not possible. So this must be 2 here. That means, and this can't be 2. So this sees 4 digits. It has to have 1 4, one more 4 here. That means this is a low here. So we have 1 low. The rest of these are middle and high digits. So this must be a 4. That's a middle digit. We have to have another 4 along this diagonal to satisfy 3 total for both modular and entropic. And then each of the other ones, one has to be satisfy the modular set, and one must satisfy the entropic set. So this can't be 4. It must satisfy either the modular set, which would be 1 and 7, or the entropic set, which would be 5 or 6. Well, this points only at 6 cells. So this can't be 7. This points at 7 cells. We'll leave that for 1 through 7 for now. These have to be either, again, 4 with 1 or 7, or 4 with 5 or 6. We're not sure which. This points at 1, 2, 3, 4, 5, 6, 7. We'll leave that at 7 also. So 1, 5, 6, or 7 there is possible. Can we have a full 6? The answer is no. Because if we tried to have a full 6, they would have to be 6 of the same entropic and modular sets. So all of them would have to be 6, but obviously we'd have a repeat here. So 5 does work as a possibility here. This can't be 1 because it's a middle or high digit. 1 has to be one of these 2 digits here. So this can't be 1 here. This 4 eliminates 4 here. If we tried to have 6 here, again, every digit on this diagonal has to either be part of the entropic set or the modular set. And 2 is not part of either. So this cannot be 6 here. Same with this. This can't be 7. 2 is not part of the same modular set or entropic set. And we can't have 6 this way for the same reasoning. This can't be 6, right? All of these would have to be a 6 here, and we'd have a duplicate here to satisfy both the modular and the entropic set. So this can't be 6. We have 1 through 5 here. Can this be 4? The answer is no. Because again, you have the same problem. You would have to have all 4 of these digits be part of the same entropic set and modular set, which would require all of them to be 4. So this is a 1, 2, or 3, which is guaranteed to be low. These are middle or high. One of these is guaranteed to be 3. So that means you would have to have 6 and 9 in the same row and 1 and 2 in the same row. Because all 5 of the digits must be part of the modular set and the entropic set. So that's interesting. Same with 1. In the same row, so okay, this is 3. This cannot be, so we have to have C6 and 9 here. We must see 1 and 2 here. So this cannot be 1, 2, cannot be 3, 4, cannot be 6, 9. So it's 5, 7, or 8 here. Right? This, okay, can't see 7 because this is already a low digit, and that doesn't satisfy the high digits here. So we have to see 5 or 6 medium cells at least. Interesting. Rest of these digits in box 2 are low and high. These are low or middle. This is low or middle. Hmm. So for 3, we know we have 2, 2, 1, 6, and 9 there. In the 3 row. This cannot be 1 because that already sees 2 low digits here. The 1 itself, so this could be 2 or it could be 3, 4, 5. This can't be 1 for the same reasoning. It sees 1 low digit already. And that would mean that would see 2, including itself. The 1 means that it does not see any of its same set here. So that would mean in the row, 2 and 3 would have to be on the other side, and 4 and 7 would have to be on the other side. So this would have to see then 5, 6, or 8. Two is interesting. 2 is the one that's going to be different. Oh, this must be missing a 2 mod 3 in this direction. So this is 1, and the other one is 5 or 8. Interesting. Um, Can this be 5? The answer is no. If it's 5, that would mean well, okay, never mind. It could be. No, it could still be 5. We know 2 has to be one of these 3 digits there. It could be 5 because it could have 2 more 5s. That's 3 that satisfy the modular set and entropic set. So you need 2 more each that satisfy the modular entropic set. So you could have 4 here. That satisfies the modular, that satisfies the entropic set. 3 doesn't satisfy any of them, so that's not going to work there. Hmm. Okay, so it could be 5 still. What about 5 in this direction? You would not have 5 5s because we have a guaranteed 2 at the bottom. And you couldn't have a absolute 5 5s here. Right? We could only have 1 5 there and 1 5 there. So that would be 1, 2, 3, 4 5s at most. Can we have 4? Maybe. Okay, let's continue with the 1, 2, and 3. So again, 3 requires... Oh, that's interesting. Okay. 3 requires these 4 digits. What do they have to be? They have to be 1, 2, 6, and 9. 1 requires these 4 digits to be what? It cannot be 2, 3, 4, or 7. So that would be 5, 6, 8, and 9. Huh. So we know one of these is guaranteed to be 6 or 9. So that means in this box, in box 3, so you're guaranteed to have 2 digits from the 1 and 2 would have to be in the same row for the 3. You'd have 5, 6, 8, and 9. So that leaves the other set as 3, 4, and 7. Because there's no other place for it in these sets, right? In the set with 3 pointing this way, it has to have all 3 of the same entropic and modular sets that its points seen. So it would be 1, 2, 6, 9, but this can't be 1 or 2. So 1 or 2 would be guaranteed here. And this, for the 1, it cannot see any of the set of the same modular or entropic set. So that means 2, 3 are removed and 4, 7 are removed, which leaves 5, 6, 8, and 9. So one of these is going to have to be 3, 4, and 7. Interesting. So the 2 will have to be pointing at the 3, 4, 7 in the row. So we'll guarantee this is 5, 6, this is 5 and 8 here. And then we have a 6 or a 9 here. So this has to have a 6, 9 pair be here. Guaranteed. 2 will be pointing at 3, 4, and 7. 2 and 3 already satisfy that for the lows. So the other digit must be 5 or 8. Interesting. So obviously no 2 there. So we have in this box, it's going to be 3, 4, or 7, all in the same row, with the same row as 2. 1 with 5, 6, 8, and 9, and 3 with 1, 2, 6, and 9. So we're guaranteed 6 and 9 are here, guaranteed. Which means the remaining digits in the box are 5 and 8 with 4 and 7. So 4 and 7 are guaranteed here. So no 4 or 7 here. This can't be 4. So 4 has to be one of those 3. Hmm. 7 obviously doesn't fit either of these. Hmm. Oh, what happens if this is 5? If this is 5, we have to have 5 be counted all the way here. Obviously, this can't be 5 here. You could have a 5 there. No, you can't. If you have a 5 here, the problem is where's 5 in column 5? So this can't be 5 either, which means we could have a 5 here, and this could be 5. But if this is 5, these are pointing at the same set of digits here, but this one's also pointing at that, which counts for the modular set, so therefore you would have guaranteed 6 5s there. So 5 could not be here in that instance. Can we then, so then we'd have to have 2 satisfying both modular and entropic arrow, but you'd have to have 3 on either side, satisfying the modular and entropic arrows there, and there's too many digits. So this can never be 5, which means this is 1 and is low. So the rest of these cannot be low. So this has to be middle, which is 4 and 5. Cannot be 4, because if it's 4, that would satisfy the modular arrow. So this has to be 5 then. So since this is 5, this cannot be 5. And the 5 again can only be part of the entropic modular arrow of 1, right? 1 is pointing at 5, 6, 8, and 9. And again, 5 has to be part of this set here. So this is 1 here, which means this can't be 1 here. This is 2 and 3. So this must be pointing at a 6 or a 9 here. And this is 6, 8, and 9 are left here. So these are high or middle. This is 5. We already have 1. So we have to have the rest be middle digits, because we already are pointing at 2 low digits here. So these are guaranteed to be all middle digits here. So therefore, this is not 7, 8, or 9. We could have one of, so these are guaranteed to be 4, 5, and 6. Well, that's interesting. None of these can be 4 because they would all be the same. That would be the same entropic modular set as 1. So we have a 5, 6 pair here. That means one of these. So this points at one of these satisfies both, and the other one only satisfies the same entropic set. So that means we have 1, 2. So these are all mid to satisfy the entropic set. The modular set, we have a 5 here. We have another 5 here. That's 2, and a 2 here. That's 3. That means these must both be 5. So this is 5, which eliminates 5 in the rest of the column. So this is 6, 8, 9 as a triplet, which eliminates 6, 8, 9 in the rest of the box. So this is 4, 7, 5, and 7 then. This is 5, 6 as a pair. And now this satisfies this set. That means this can't be 5 here. There's no 5 there. Okay. 5 eliminates 5 here. So this is 3, which means that's 3 in the corner. We celebrate because we're close to solving this. Remaining digits of column. So of column 6. Well, 1 can't be here. 4 can't be here. This must be a 1, 4 pair here. So that's low and middle. That leaves the remaining digits as 3 and 7. This can't be 3 because of 3 in the row. So this is 7. That's 3. That eliminates 7 in the rest of the box. So this is low. This is high. Remaining digits then in box 9 are 6, 8, and 9. Five eliminates 5 here, so that's 6. Oh boy. That means we need 3. We have how many possible 6s? 1, 2, 3, 4, 5. 5 6s, and then we have 1 satisfying the entropic part and 1 satisfying the modular part. So that's what that's going to have to do. So then we have to have a 6 here. This is middle again. That means we have 3 middles in row 7, which eliminates middles in the rest of the row. So these are both high, and this is low and high. So this is definitely a 6. We need a 6 in every possible box. So this is not high, which means these can't be middle because we have all the 6s in column 5. This then 4 must be a 6 and is middle. This is 6. This is 6. So no high. And one of these is a 6 here. So this cannot be 6. We have 8 and 9, which are both high. So this must satisfy either the modular or the entropic. It can't satisfy the entropic, so it must satisfy the modular. So is 3. And this must be 6 with the other satisfying the modular. So these have to be both middle, which means this is 4, 6 as a pair. That eliminates 4 in the rest of the box. So this is low, and it's 2 or 3. Remaining digits in this box then have to be 7, 1, 2, 3, and 7. So we have a 2, 3 pair here, which eliminates 2 and 3 in the rest of the row. So this is 1 or 7. That's fine. 6 eliminates 6 here, so it's 8 and 9. So these are both high. Five eliminates 5 here. Remaining digits in this row have to be 2, 3, 4, and 7. 2 and 4 cannot be here because of 2 or 4 in the column. 3 can't be here because of 3 in the column. Okay. This is 7, 8, or 9 there. This could be 5, 7, 8, or 9. This sees 3 lows and 3 0 mod 3s. Well, 2, 4, and 7 are not 0 mod 3. So these must be 0 mod 3s here. So this is 3, 6, and 9. Cannot be 3 or cannot be 6. So that's 3 or 9. And this is 3, 6, or 9, guaranteed. We have a guaranteed 6 here. Okay, 6 eliminates 6 here. So this is 5, which makes that 6. 6 eliminates 6 here, so that's 4, which makes that 6. So this part must be 3, 4, and 7. So this is 3, that's 7. That leaves this as a 1, 2 pair, which are both low. This is high. 3 eliminates 3 here, so that's 2, which makes that 3. 3 must have all of these digits be part of the modular set. 4 and 7 eliminate 4 and 7 here, so that's 5. 2 is pointing at 2 lows, and only these are not the same modular set, so this must be 8, and that's 9. This is 5, which eliminates 5 here. Remaining digits in row 2 cannot be 3, so it's 1, 6, and 9 here. 6 cannot be either of these digits because of 6 in the column. That requires this be a 6 there. So this is middle, which means this has to be 3 lows here to satisfy the lows because it doesn't satisfy low there. Therefore, this must be 2. That means this must be 3. So this can't be 3, that's 7, which makes this not 7, that's 4. This can't be 2, 4, 7, it's 3. So again, we have low, this is middle, this must be high, and is 7. This is high. So which ones are satisfied? Remaining digits in row 1 are 4, 5, and 8. This can't be 4 because of 4 in the column. So let's make sure everything's satisfied. 3, pointing at 1, 2, and 3. That's 3 low digits for entropic. 3, 6, and pointing at 3, 6, and 9. 3 0 mod 3s digits there. 2, pointing at 2 and 3. 2 low digits. And 2 and 8, 2 2 mod 5 digits. 1, pointing at 1 itself. Does not point at 2 or 3, does not point at 4 or 7, so that satisfies that entropic and modular set. 5, pointing at 5, 5, 5, 5, and 6, that's 5 middle digits for the entropic, pointing at 4 5s and a 2 for the 2 modular 3 digits. These digits are middle and high. These digits are low and high. We have one of these is a 2. The other one has to be a high. So we have low and high here and low and high here. Okay, 2 is pointing at 2 2s and a 4, which doesn't satisfy. 4 does not satisfy modular or entropic. So 2 is satisfied there. 3, 1 is satisfied. It's pointing at no 4s or 7s, and no 1s besides itself. 2 is satisfied, and 3 will be satisfied. Okay. We have 8 3s. We know where the last 3 has to be. It has to be there. 2 eliminates 2 here, so it's 1. That's 2. This is 3 and is a low. So we have remaining digits are 4, 5, 7, 8, 9. 5 cannot be here. So this must be high as a 7, 8, 9. So this is high or 7, 8, 9. 5, 7, 8, 9. 7, 8, 9. No 7 here because of 7 in the row. Where's the 9 in row 9? It has to be one of these 2 digits, which eliminates 9 in the rest of the box. This digit has to be 5, 8, or 9 also. Cannot be 5 because of 5 in the column. So we have an 8, 9 pair now in column 8, which eliminates 8 and 9 in the rest of the column. That leaves us 1, 2, 4, and 7. 2 cannot be here because of 2 in the box. 4 can't be here because of 4 in the row. 1 can't be here because of 1 in the row. So these are both middle and high. Three is pointing at itself in the 2. So it must be pointing at one more low. We don't have anything else here. This doesn't satisfy the entropic or modular set. It's 4, 5, and 8. This 3 is satisfied. 3 is pointing at 3 lows in 3, 3, and 2. It's pointing at 3 0 mod 3 sets, 3, 3, and 6. So this is done. So we just have these 2. Okay. This doesn't satisfy either. This satisfies just the low. This cannot be. This is 2, 8, or 9 here. Interesting. Remaining digits of column 9. We have 1, 4, 6, 8, 9. 6 obviously cannot be any of these digits because of 6 in the box. 6 can't be here because of 6 in the row. This can't be 4 because of 4 in the row. So where is the 6? It has to be here. So this is high, not high. This is middle. We have a 5, 7, 8, 9 quadruplet in row 8, which eliminates 5, 7, 8, 9 in the rest of the row. So this must be 4 and is middle. That eliminates 4 in the rest of the column. So this is guaranteed to be low or middle here. Four and 5 don't satisfy the entropic or modular arrows. That means one of these has to be a 9. Because we don't have a 3 anywhere on this diagonal. And 6 is no longer there too. I think all the 6s are taken. Seven eliminates 7 here. Remaining digits in column 3 are 1, 5, 8, and 9. Okay, so we have just this and this. We have 2 3s. We do not have another 3 on this, so we need one that satisfies entropically. It's not going to be here. We have 3 and 6 already accounted for in those boxes. So we don't have any of those. This can't be 9 because of the way that this works. So we're guaranteed to have a 9 here, which means this cannot be 9 here. This can't be 9 there. Oh, wait, that's not true. You could have a 9 there. We also need a low on this diagonal. So we have either a 9 here or a 9 in one of these two cells. And it cannot be both. Interesting. What about this diagonal? We either have a 9 here. We need one more low, so either this is 1 or this is 2. And we need a 9 on this diagonal. So either this is 9 or one of these is 9. But that doesn't help us much. 6 eliminates 6 here. Oh, we're not done with this one. That's interesting. This can't be 6 because of 6 in the box. This can't be 5. Oh, we know this is satisfying the modular set. So this has to be 2 middle digits to satisfy the entropic. So this cannot be 1 or 7. It's 4. This can't be 1 or 7 or 4. It's 5. Okay, that's helpful. So 4 eliminates 4 here. We have a 5-8 pair here, which eliminates 5 and 8 in the rest of the row. So this can't be 5 or 8. It's 4. This is not high. We have all 3 middles here. So this can't be middle. It's 7 or 8. This can't be 5 either because of 5 in the column. So 5 is one of those two. 4, 5. 4 eliminates 4 in the rest of the row. How many 5s do we have? We don't have enough. Okay, so this is satisfied. This points at 3 4s, which satisfies 3 of the entropic and 3 of the modular. 1 gives you the other modular. 5 gives you the other entropic. So this is done. Remaining digits of box 4 are low and high. Remaining digits here are 1, 2, 7, 8, 9. So 2 can't be here. Okay. 4 is one of those two. Where is 2 in row 5? Can't be here because of 2's in the column. Can't be here because of 2's in the columns. Can't be here because 2 in the column, so 2 has to be there. And is low. So this cannot be 2 anymore. It's 1 or 7. Okay. I think I just have to go down the path and just basically see what happens, right? Just trial and error. Otherwise, I don't really see any other way of really solving this. Yeah. So this doesn't satisfy either for the 3 there. This satisfies 2 of them. We need 1 low and 1 0 mod 3 along this diagonal. We have 2 satisfying low, so we need 1 more satisfying low here. Oh, we need 2 more satisfying 0 mod 3s here. There we go. So only one of these can be 9. So this has to be a 9 here. So this is 9, which makes that 1. This is not low. This is not high. So that eliminates low there. So that satisfied the 0 mod 3, and then we need 1 more 0 mod 3 and 1 more low. So this has to be low, which means this can't be low here. And this has to satisfy the 0 mod 3s. So therefore, this is 9. That's 2. This satisfies the other 0 mod 3. 2 and 9 eliminate 2 and 9 here, so that's 8, which makes that 7. 9 eliminates 9 here, so it's 8 and 9. We have all the 0 mod 3s on this diagonal, so this can't be 9. That's 8, that's 9, which makes this not 9, that's 8. So I think this should be satisfied. 3 is pointing at 3, 2, and 2 for the lows, and 3, 9, and 9 for the 0 mod 3s. We just need to figure out the lows here. 9 eliminates 9 here, so that's 8, which eliminates 8 here, so it's 5, which makes that 8. 5 and 8 eliminate 5 and 8 here, so it's 9. So this cannot be 9 here. It's a 7-8 pair here, which eliminates 7, 8 in the rest of the column. So this can't be 8. This is 1. This can't be 1 or 8. It's 5. So no 8 here. No 1, 7, 8 here. It's 2 and 9. 2 eliminates 2 here, so that's 9, which makes that 2. So let's figure out what these entropic sets are. Middle, this is not middle, that's high. This is not low, this is not high. This is low, this is middle. Okay, 7 eliminates 7 here, so that's 1 and 7. That means this is not high, this is not low. This can't be high because we have 3 highs in the row. So this is 1, no 1 here. That leaves this as a 9, so no 9 here. This can't be 9. 7 and 8 eliminate 7 and 8 here, so it's 5. This can't be 5 or 8. It's 9. No middle, no high. 8 eliminates 8 here, so that's 7, which makes that 8. This 3 already points at 3 lows, so this cannot be low here. It's middle. This can't be middle then. It's high, low. Low eliminates low there, so that's high. This can't be high then. That's low. That leaves 3 middles, so this can't be middle. This has to be high, which makes that middle there, and this is high. So then just solving for everything, this is 7. This has to be 4. And let's just make sure this satisfies everything. 3 is pointing at 1, 3, and 3, all the lows. It's pointing at 3, 3, and 9 for the 0 mod 3s. So that's satisfied. 4 eliminates 4 here, so it's 1, which eliminates 1 here, so it's 7, which makes that 1. 8 eliminates 8 here, so that's 4, which makes that an 8. And that's a solution. Pretty interesting, actually, how these arrows interacted with themselves, really. It was pretty limiting on what they could actually be pointing at, which was interesting. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.